Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. Today, we are doing a deep dive into the concept of inductance from your Unit 6, electromagnetic induction. And we promise a very simple, exam-safe explanation that will make this topic absolutely crystal clear for you. Okay, so let's start with a simple question, something you've probably seen many times. When you quickly switch off a major electrical appliance, maybe a motor or even just an old fan, have you ever seen a little spark at the switch?
Oh, yes, definitely. I always see that, especially with the older switch. I just thought it was, bad wiring or something mechanical.
That's what most people think, isn't it? But here is the amazing thing. That spark is actually caused by a massive momentary voltage induced by the circuit itself. The circuit is fighting its own change in current.
Wait, what? How can the circuit induce a voltage when the main power is cut off? There's no battery, no external power source forcing the current at that moment. So what is causing that high voltage flash?
Exactly. That is the counterintuitive part. The circuit is fighting to keep the current going. And this resistance to change, this property, is what we call inductance. So let's define the core idea. At its simplest level, what is it? Inductance is the property of an electric circuit that opposes any change in the current flowing through it. It's a measure of how effectively the circuit resists rapid current changes. And it does this by inducing a counter EMF.
A counter EMF. Okay, but I think an analogy would really help here.
Absolutely. The best analogy is a heavy flywheel, a big, heavy disc on a motor shaft. When you try to start it up, it resists your push, right? It's hard to get it spinning.
Yeah.
That resistance to starting up, that's like inductance, resisting a current increase. But then once it's spinning really fast, what happens if you try to stop it suddenly?
It keeps wanting to turn. It fights you.
It fights you. It has inertia. Inductance is the electromagnetic version of that mechanical inertia. It resists a current decrease just as much. And you asked why it exists. It's not about physical mass. It's about the magnetic field. See, current creates a magnetic field. When the current changes, the field changes. And Faraday's law tells us a changing magnetic field induces an EMF. That induced EMF is what pushes back. For a mental image, just picture a solenoid. Think of it as storing magnetic momentum in its field when current flows. When you try to change that current, this magnetic momentum pushes back. It's like a built-in brake on any current variation.
Okay, that helps. But then what's the difference between self-inductance and mutual inductance?
Great question. It's the same principle, just a matter of location. Self-inductance is the coil fighting its own current change. Mutual inductance is when one coil's changing current affects a neighboring coil. It's like its inertia is spilling over and affecting the coil next to it. All right, now that we have the feel for it, let us see how insert defines this and formalizes the mathematical relationship. We have to be ready for the exam after all. Could you read the definition from the textbook for us?
Of course. Insert says, inductance is the ratio of the flux linkage to current. It is equal to N times phi B divided by I, and it says the unit is the Henry, which is H.
Perfect. Let's break that down step by step for self-inductance, which we call L step 1. A current, I, flows in a coil and creates a magnetic flux, phi. The total flux linkage is just N times phi, and it's directly proportional to the current. Simple. Step 2. To make it an equation, we need a constant. That constant or proportionality is L, the self-inductance. So we get our formal definition. N phi equals L times I. Now, step 3 is the most important part. When that current I changes, the flux changes, and Faraday's law kicks in. An EMF is induced. And this leads us to the main formula we use. The induced EMF is epsilon equals minus L times di by dt.
It looks a bit scary.
It's just a way of saying the rate of change of current. That's all.
Yeah.
So the faster you try to change the current, the bigger d is, and the bigger the opposing voltage becomes.
Ah, I see. And the negative sign, what does that mean?
That's just Lenz's law. It's a crucial point. The negative sign means the induced EMF always opposes the change that created it. If current is increasing, the EMF pushes back to slow it down. If current is decreasing, the EMF pushes forward to try and keep it going. That's our spark. And remember, L itself depends only on the geometry of the coil, its shape, its size, the number of turns, and the material inside it. Hope everything is clear so far. This concept explainer is from ProfSam.com, that is ProfSam.com. Let's do a very quick example, just to see the numbers. Suppose a solenoid has a self-inductance L of 0.5 Henry, not very large. And let's say the current changes from 2 amps to 0 amps in just 0.1 seconds, so you flick a switch off.
Okay.
We want the magnitude of the induced EMF, so we use the formula magnitude of epsilon is L times delta I over delta T, so that's 0.5 multiplied by, well, the change in current is 2 and the time is 0.1.
So 2 divided by 0.1 is 20, and half of that is 10 volts.
10 volts. C. Even a small inductance can create a significant voltage if the change is rapid enough. That explains the spark perfectly. And this leads to a very important connection for our next topics. This resistance to change. It means work has to be done to build up the current. That work, that energy doesn't get lost. It gets stored. It's stored in the magnetic field itself. And the formula for that stored energy is U equals half Li squared. This idea is central to understanding AC circuits. All right. Now we have to talk about the silent killers, the common mistakes that cost students marks. Misconception number 1. Many students think inductance resists the current itself, just like resistance.
Right, I can see that. They both seem to oppose things, so
Yeah.
they're not the same.
Not at all. That's the trap. A resistor fights current all the time, steady or changing. It just turns energy into heat. An inductor, it only fights changes in current, the DID part. Once the current is steady, a constant DC current, DID, is 0. And an ideal inductor acts just like a simple wire. It does nothing.
So a steady current is not affected by inductance at all. It only cares about the starting, the stopping, or any fluctuation.
Exactly. Now, the second confusion is about the term backemph. It sounds negative, like a bad thing. But physically, self-inductance is the electromagnetic analog of what?
Mass or inertia.
Yes, it's inertia. And inertia isn't a bad thing. It's what ensures energy is stored, not just wasted. So here's the hook to remember. A resistor fights current. An inductor fights change. Okay, let's lock this in with some memory anchors. First, a little mnemonic. For when an inductor is happy with a steady DC current, just remember, L loves I steady.
L loves I steady. I like that.
Second, a strong phrase to remember what it does. Coils hate sudden current. Simple, but powerful. They will fight you if you try to change the current suddenly. And finally, a physical gesture. Try this. Sweep your arm out slowly. Now try to stop it instantly.
Whoa.
Feel that resistance to the change, that feeling that is high inductance, resisting the start and the stop. Okay, so we've covered a lot. Let's wrap up with an exam, say 3-point summary. Point 1, inductance, L or M, quantifies how a circuit opposes changes in current by inducing a counter EMF. The formula is epsilon equals minus L didt. Point 2, inductance depends only on the coil's geometry, its shape, size, number of turns, and the permeability of the core material. It does not depend on the current. And point 3, physically, inductance is electromagnetic inertia, just like mass in mechanics. The energy used to build the current is stored in the magnetic field, given by U equals half Li squared. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is ProfSam, right?
Yes, ProfSam.com. Thank you so much for joining us. Keep studying hard, and we'll see you in the next one.